Hello and welcome to our Chapter 39 video lecture series. In this video, we are going to talk about Section 2 on gas exchange across respiratory surfaces. And our learning objectives are to name and describe lung volumes and capacities, understand how gas pressure influences how gases move into and out of the body. So let's start with the principles of gas exchange. We know that we need oxygen in order for our mitochondria to produce ATP. So it has to be supplied to all of our cells, and as a waste product from our cells, we need to remove it from our body. So respiration is going to include an exchange of gases, not only in the area of the lungs, but in all of our tissues that need that oxygen. So we have to know the principles of diffusion, and that really decides whether the oxygen is going to enter or leave the blood, and same with our carbon dioxide. And our gases exert pressure, and all of that pressure it exerts is called the partial pressure, and we symbolize it as a capital P with a subscript of the gas element that it is representing. So for carbon dioxide, we have the partial pressure of it here, and partial pressure of oxygen denoted that way. So if this partial pressure of gas differs across a membrane, it's going to diffuse from an area of higher pressure to lower pressure. So we see this in the alveolus of the lung. So let's actually start on this side. When the partial pressure goes up in the alveolus, because we have all of this oxygen in our lungs, it is going to diffuse out of that alveolus and into our blood capillary where that partial pressure of oxygen is lower. It's at 40. And we see a difference here for carbon dioxide. We have the waste product of carbon dioxide in our capillary at a partial pressure of 45, but in our lungs, we have a partial pressure of carbon dioxide at 40. So naturally, this is going to diffuse toward the alveolus, and we can breathe that carbon dioxide out. Now we can measure our lung volumes and capacities using something called spirometry. So that helps to measure the volumes of air that move in and out of our respiratory system. And we get a readout, something that looks like this. And we start off with the tidal volume. This is just us normally breathing, inhaling and exhaling. It's going to be about 500 milliliters, but this number does vary and change depending on your age, your biological sex, your height, and your fitness. Then we have our functional residual capacity. I forgot I had little highlights here. So our functional residual capacity is the volume of air that remains in our lungs at the end of normal expiration. And in a moment, well, actually, I don't think I have it on the next slide, but this is going to include this residual volume. So the residual volume is the amount of air that we have within our lungs that we cannot exhale. We cannot get rid of it in our body. So that is coupled with what we're going to talk about on the next slide, the expiratory reserve volume, to give our full functional residual capacity. But before we get to that, let's talk about the inspiratory reserve volume. This is the amount of air that we can forcefully inhale after normal inspiration, and tends to be around 3,000 milliliters at rest. But it can range from 2,100 to 3,200 milliliters. So let's get back to that expiratory reserve volume we were talking about. This is the amount of air that we can forcefully exhale after normal expiration. It's really combined with this residual volume in order to get that functional residual capacity. And like we said, we cannot exhale this volume out of our body. It's really there in order to keep our alveoli open. And then we have our vital capacity, and this is going to be the amount of air that can be moved into and out of our respiratory system in a single respiratory cycle. So it is going to include our inspiratory capacity, which you could see labeled over here, combined with our expiratory reserve volume, or we can kind of separate out that inspiratory capacity and say that it includes our inspiratory reserve volume, the tidal volume, and expiratory reserve volume. Essentially, it is all of this area excluding the residual volume. And here's just another figure that is color-coded that I thought might be helpful, going through these different volumes and capacities, and it kind of gives you a formula here to calculate what these volumes or capacities would be. So use this to however you would like. And let's also talk about our forced expiratory volume. So this will measure how much air we can force out of our lung, but it's over a specific period of time. Usually we do it over 1 second. So this is called FEV1. And then we have our forced vital capacity, and this is the total amount of air that could be forcefully exhaled. And so what we do is look at a ratio of this FEV1 over FVC, and it's used to diagnose lung diseases, including asthma, emphysema, which would be COPDs, and fibrosis. So when we have our normal FEV1 over FVC ratio, we see that it should be above 75%, but it does depend on your age. For instance, for people who are older than 65, the normal percentage would be 65%. Now, if your ratio is high, it may signify that the lungs are not compliant, meaning they're stiff and unable to bend properly. Most likely, these patients have some type of lung fibrosis taking place, and the patients are going to exhale most of the lung volume very quickly. And people with this type of condition could be classified as having a restrictive lung disease, and other times, even if their ratio is normal, they may still have this restrictive lung disease going on. If this ratio is low, there is resistance in the lung, and this could be characteristic of asthma or other chronic obstructive lung diseases. It's hard for the patient to exhale and essentially takes a long time for them to reach their maximal exhalation volume. So you may see ratios that are between 45 and 60% here. Essentially, anything that is less than 70% is suggestive of airflow limitation with an obstruction type of pattern. So let's revisit the gas pressure that we were talking about earlier. Now, when we look at atmospheric pressure, this is the pressure of the air in our environment, and it's going to equal 760 millimeters mercury. And that is created by all the gases we have within our air. You can see that nitrogen makes up about 79%, oxygen is about 21%, and there's a little bit of carbon dioxide in our air. There's also a bit of water vapor. It makes up about less than 0.5%. And this pressure can change with altitude. So when we get an increase in altitude, you may hear it being described as thinner air, meaning that there's less pressure than what we see at sea level.